It's a pleasure to introduce Fatemeh Mohammadi from Ghent University, and she'll talk about a fiber-based approach to triangulations of Amplituhedron.
Okay. Hi, everyone. Thank you so much for having me here. It's a pleasure to be here. So I'm basically like participating in the workshop to learn more from you guys. Thank you. So, okay, so let me start off by the main object of the study here. So namely the Amplituhedron, introduced by Nima Erkani-Hamed, Yaroslav Trenka in 2013. And as you know, so the geometric invariance, the geometric properties of this object is somehow like the object of the study. So namely, we would like to understand the volume of this geometric object and various invariants associated to it. Most importantly, the canonical form of the Amplituhedron, which is this geometric object Amplituhedron comes with a unique top degree rational form whose poles are simple and they all happen like along the boundary of this object, and we would like to understand this canonical form and compute them. Okay, so a kind of reformulation of computation of this canonical form is given in terms of finding subdivisions of this geometric object. So from mathematical point of view, so then these are the questions, like how to compute the canonical form of the Amplituhedron, how to find different triangulations, subdivisions of this object, and how are these different triangulations are related to each other. Okay, so let me give you an overview of what we will see during this talk. So as we said, the main goal is to understand the Amplituhedron, but we are going to look at the more general object defined again by Thomas Lamb, Erkani-Hamed here, that they looked at positive geometries. So the goal is that you have two spaces, projective varieties, let's say x and x prime. So they're larger spaces and they come with some distinguished subsets. Let's denote them by x plus, x prime plus. And then you have a map between these distinguished subsets, and then you would like to understand the image of this map. Okay, so I have a map from x plus to x prime plus, and then I would like to understand the image of this map and then see what properties of x plus kind of is transferred to its image. So these properties could be somehow related to this canonical form that we would like to understand, or different kind of subdivisions of the original object. Okay, so the approach we are going to take here is by studying the fibers of these maps. Namely, we are going from fiber geometry perspective, so we are going to look at the extension of this map pi plus. So instead of looking at the image of this map, so we are going to extend it to this large space between like x and x prime, and then basically look at the fibers and the pre-images of this map. Okay, so what do I mean by that? So you take like any point like in the image, and then you look at the pre-image of those points, like both under these pi plus and also pi map. And then you would like to see what sort of geometric properties these fibers have. And we will later see the kind of a more concrete definitions of the positive geometries, but from that perspective, so we wanna see that these fibers are themselves nice and they form like positive geometries as well. So in particular, so we would like to understand the fibers of defining maps of the Amplituhedron. So namely, to define the Amplituhedron, so we have this map x plus between positive Grassmannian and the Amplituhedron, and the extension would be like a rational map between different Grassmannians, and then we would like to look at the fibers of this map and then see what properties they have. For example, so we will see that if you know these fibers, so they also come with a unique top degree rational forms, similar to these the canonical form of the Amplituhedron, and certain kind of residues of these fibers lead to computations of the canonical form of the Amplituhedron. And in very specific cases, like in the case of polytopes, in terms of the conjugate of polytopes, these fibers are kind of nice in a sense that their denominators is a product of linear forms, and then you can see these linear forms being corresponding to some hyperplane arrangements and some polyhedral fans, and these fans have all the necessary information that you would like to find all subdivisions of Amplituhedrons. So basically, for those specific cases that we will see that these fiber these fibers kind of encode all different triangulations and all the information that you need to compute the canonical form of the amplituhedron. Okay, good. So now let me give you an overview of what we will see next. So I'm going to start by giving you some examples of amplituhedron. So namely, the simplest example are polytopes, cyclic polytopes, and positive Grassmannians, that they are well understood in terms of the triangulations, in terms of the canonical form. Then I show you the more kind of concrete, formal way to define the amplituhedron, and then see what sort of properties of amplituhedron we are interested in, namely triangulations, their canonical forms, and then we will look into positive geometries and these fibers of positive geometries and fibers of amplituhedron. Okay, so let me start easy, by looking into polytopes, that they are somehow the simplest example that we can see from for these amplituhedron. So for polytope, so what do we mean by subdivisions or triangulations of the polytope? Somehow, let's take this pentagon, and the subdivision of the polytope is just a finite union of polytopes. So that means how many ways I can kind of subdivide my polytope to kind of smaller polytopes. But at the same time, I would like to have these properties that whenever I take a pair of subpolytopes, so they intersect nicely. So either they're disjoint, they don't overlap, but when they intersect, so the intersection is on a common proper face. So for this case, this easy example, we see that we have 5 different triangulations, 5 different ways that you can triangulate your pentagon. And actually, you can even do more. So there are kind of subdivisions of these pentagon that you can divide it to a fourgon and a triangle. And there are also kind of, you can see them in this picture. And more generally, so we would like to understand all subdivisions at once. And this work has been done, started by Gelfand, Kapranov, Zelewensky back in 1990, when they studied the secondary fan of polytopes, which is the polyhedral fan, whose faces corresponds to different subdivisions of your polytope. For example, these polyhedral fans are pointed, so the center corresponds to the polytope itself, and the rays here are corresponding to various subdivisions, and the maximal faces or the cones in your polyhedral fan are encoding the triangulations of the polytope. Okay, good. So what are the examples of polytope that they show up as amplituhedron? So they are cyclic polytopes. They are even nicer. So there are specific families of polytopes that you can construct in terms of the convex hull of any n distinct points on the moment curve. So you take any moment curves in RD, you evaluate it in n different points, you take the convex hull, and then you have a cyclic polytope. And the triangulations, the subdivisions of cyclic polytopes are also well studied. For example, they have similar combinatorial type, no matter what kind of points that you have chosen from the beginning. So the combinatorial data that you obtain for these polyhedral fans are going to be the same. Okay, and as we saw, so the secondary fan of polytopes are in general well understood, and the triangulations of these polytopes are corresponding to the maximal dimensional cones of the secondary fan. And just one easy way to see how you can construct this fan is by Gale duality, Gale transformation. So basically, whenever you have a polytope or projective polytope, like in this example, whenever you have n points in Rm, this Gale transformation transfers these n labeled points in Rm to n labeled points in Rn minus m, and then these are going to be corresponding to the rays of these polyhedral fan in this picture. So, and then you have the rays, and then you look at the chamber fan, you construct the polyhedral fan, which is the secondary fan of your polytope, and encodes all these subdivisions. Okay. So that was the first example of amplituhedron. So the second example would be the positive Grassmannian that we already saw many times also yesterday. So what is to define the positive Grassmannian? Let me first recall the notion of Grassmannian Kn, which is the set of k-dimensional subspaces, either you can take complex numbers or real numbers to define the Grassmannian. And basically every element of Grassmannian can be represented by a full rank K times N matrix. Okay, and then of course two different matrices might lead to the same subspace. So we would like to look at the set of all these full rank K times N matrices up to GLK action. So here is an example in Grassmannian 2, 3. So I take 2 times 3 matrix X, and then for every such matrix K times N matrix, so we can also define so-called Pluhar coordinates that they are indexed by the maximum by the collection of K columns of your matrix. Okay, for example, here I have two subsets. So for 1, 2, so I look at the Pluhar variable indexed by 1, 2. So that would be the minor of the corresponding submatrix. Okay, and now positive Grassmannian is defined to be the set of all elements of Grassmannian Kn such that they have this property that whenever you compute their Pluhar coordinates, they are all going to be non-negative. Okay, and they have been studied a lot from also, we've seen these positivity properties that they show up like in yesterday's talk, like in Pavel's talk, they show up like in cluster algebra and many more different contexts. Okay, so now the question is, now you have this positive Grassmannian, can you find like a nice decompositions of this geometric object? Okay, again back in 1987, Gelfand, Goreski, McPherson, Sarkonova, so they had this nice matroid stratification of Grassmannian Kn that basically for every Grassmannian Kn you can decompose it in terms of certain matroids that could be kind of complicated, like each component could be also very complicated. But then later Postnikov showed that if you restrict this matroid stratification to positive Grassmannian, so that behaves much nicer, and actually so you get like a cell decomposition of the positive Grassmannian. Okay, so what are these cells? So they are called positroid cells, and to define positroid cells we are going to take you can take like any collection of K subsets of 1 to N, okay? And then for every such collection M, you can define a positroid cell, which is the collection of all matrices in positive Grassmannian Kn, representing elements of positive Grassmannian Kn, such that the corresponding Pluhar coordinates are only non-zero if the index set comes from your set. Okay, so these are positroid cell. Of course, if you choose them, the collection badly, so it's also possible that the corresponding cell is empty. And what is shown is that every non-empty positroid cell is a topological cell homeomorphic to an open ball. And the positroid cells somehow glue together nicely and they form a CW complex, namely the positive Grassmannian. Okay, so yes, now let me formally define the amplituhedron. So the amplituhedron is the image of the positive Grassmannian under a linear map. So to define it, so we need 3 parameters like n, k, m, and then we also need like a matrix Z, which is the n times k plus m matrix with positive maximal minors. Okay, so and then you can define and then you can take like a map from positive Grassmannian Kn to Grassmannian k plus m by matrix multiplication. That you take any k times n matrix in positive Grassmannian, you multiply it with Z, and you get like a matrix k times k plus m matrix, and the image of this map is defined as the amplituhedron. Okay, so now as you see, the definition depends on the choice of Z, but it's been conjectured that the combinatorial, the geometric properties of these objects are independent of the choice of Z. In particular, different sort of in the polytope case, so that was evident that for the cyclic polytope case, no matter what kind of points you take, like in the moment curve, so the corresponding secondary fan was independent of the choice of the points, or the triangulations are kind of fit nicely together like in the secondary fan. Okay, so what are the properties of amplituhedron? So first of all, so that's the image of the positive Grassmannian in Grassmannian K plus M. So it's a semi-algebraic subset of Grassmannian K plus M. So that means it should be defined by a collection of polynomials, by a collection of inequalities somehow. That it would be nice to have the precise description of the boundary of the image of the amplituhedron. So also you can easily see that it's a full dimension, so it has dimension km in Grassmannian K plus M. And also since this is the image of positive Grassmannian, and the positive Grassmannian has this nice decomposition into positroid cells, so the expectation is that the image, or the idea is that to find like the collection of positroid cells whose images can be also used to decompose the amplituhedron. Okay, so this is the idea, somehow to use the positroid cells and their images to subdivide the amplituhedron itself. So, and of course there are a couple of problems like arising. First of all, so the image of positive Grassmannian is a full dimension Km, but it's not necessarily true for every positroid cell. So if you take like a positroid cell, arbitrary positroid cell, and then you look at the image, so it might have lower dimension. So you have to find or characterize like those positroid cells whose image will be of the correct dimension. Okay, so that would be then the question, to find somehow collections of these positroid cells whose image triangulate the amplituhedron. Okay, so good. So these triangulation subdivisions of amplituhedron has been studied a lot, and in particular, like once you are like in the polytope case, so the triangulation subdivisions, the one that we saw in the beginning, so kind of makes sense, had a precise definition. So here, so I would like to recall what is the notion of triangulations of the amplituhedron, because the amplituhedron is no longer a polytope, is not necessarily like a polytope. Okay, so the definition is that you need to find like a collection of positroid cells that once you're looking at the image, first of all, so the image is of the right dimension, so it has a full dimension. And of course, if you want to triangulate or subdivide your space, you want the images of these cells to kind of be pairwise disjoint and cover a dense subset of your amplituhedron. And also, we want this we want the map to be injective, like on every positroid cell. Okay, so now the question is, like in the polytope case, whenever you were looking at the different sub-polytopes, like covering the polytope as a subdivision, so we also had this property that whenever two of them overlap, so the overlap should be like along the common face of these two sub-polytopes. So here you can ask, what does that mean for two cells to overlap or to have the common boundary? And this definition has been made precise by looking into good triangulations. And by that, we mean like whenever you have two positroid cells, and then you look at their images, and their images have intersection, like in codimension 1, so you want the intersection to be also the image of a third positroid cell, which is in the intersection of the original pair. Okay, so this has been defined to be as a notion of good triangulations. And from polytope point of view, so these good triangulations are somehow related to these regular triangulations, that they fit like in the secondary fan structure. Okay, so let me just go back again. Look, so far we've just seen two examples, families of examples of amplituhedron, so namely the cyclic polytopes with n vertices in PM, so like the projective polytopes. And then we saw that in this case, you can actually construct concretely like a collection of all these subdivisions of polytope. So namely, you would take like these points, like the vertices of in Rm, and then by Gale transformation, you can convert them to endpoints like in Rn minus m, that they are kind of the rays of this secondary fan here. And then you construct, and then you look at different cones and different subsets, different faces of this polyhedral fan, and these are encoding all these subdivisions, and also they show like how these subdivisions are related to each other. So you can basically move from one maximal cone to another one by kind of flipping some of the triangles. Okay, and then we also saw this notion of positive Grassmannian as another example, which comes with a natural decomposition into positroid cells. So what are the other examples that have been studied in this context? So of course, the main case of interest for physicists is the M4 amplituhedron, but also these are cases like M1, M2 that they have a very nice description from mathematical point of view. For example, the M1 case, it's going to be homeomorphic, the amplituhedron M1 case, so it's homeomorphic to the bounded complex of the cyclic hyperplane arrangement. So this has been studied by Stefan Karp, Lauren Williams. Or the M2 case, there are a series of nice papers recently, just in the past year, that the M2 case is related to hypersimplex and tropical positive Grassmannians. So somehow you have a fan structure. You can compare this fan structure of the amplituhedron to the structure of the fan of the hypersimplex. And also another nice families of amplituhedron that have been studied are in connection with this periodic conjugation that you have. This is a work by Galashin and Thomas Lamb that they showed if you have for every pair of amplituhedron that they are conjugate to each other, namely ANKM and N minus M minus K, so they kind of worked out what are the connections between their triangulations and their subdivisions. Okay, so these are kind of nicely connected, and motivated by this, we actually looked into the case of polytopes and conjugate to polytopes. We wanted to see whether we can make these connections between triangulations even more precise, and also the fact that somehow for the polytope case, you have this nice secondary fan structure which encodes all these kind of subdivisions of the amplituhedron. We wanted to see whether we can construct such a fan for the conjugate to polytopes that they are no longer polytopes. And it turns out that there is indeed a well-structured notion of secondary amplituhedron for conjugate to polytopes. So, and the construction is kind of related to looking at fibers of the amplituhedron that I was telling before, and I would like to discuss this more like in details, that how looking into fibers of amplituhedron helps us to understand the geometry of these objects even better. Okay, so maybe this is a good place if I pause, and if there is any question, please feel free to unmute yourself. I know I was super fast, so I have to stop now.
I have a question about the M equals 1 case when you say it's homeomorphic to the bounded complex. So yes. I was under the impression that it's actually the bounded complex. What's the nature of this homeomorphism?
Yeah, I'm not sure. I think it's not exactly, so it's yeah, I'm not sure, but if Lauren is here, so that's her paper, so maybe she can say something.
Sure, I'll just say that the computer lives in projective space. So
okay.
Oh, it's similar to when we are talking about the polytope case. We are talking about the projective polytopes.
But that's all. I mean, it's more or less exactly the bounded complex.
Yes. Yes.
Okay, got it. Thank you.
Thank you. Yeah. So, any other question? Okay, perfect. So, okay. So now, because I would like to talk about these fibers of amplituhedron, so it makes more sense for me to go to the more general framework of positive geometry and then speak about the fibers of positive geometries. So again, these positive geometries have been introduced by Arkani Hamed Trenko, Thomas Lamb, and I've learned a lot about these positive geometries by actually watching some of the nice lectures by Thomas Lamb that I would like to thank him in particular. So, okay, so what are positive geometries? So basically, to define a positive geometry, you can define it recursively as a pair of, let's say X and a distinguished subset like X plus. And it has this property that whenever you're looking at the boundary of the positive part, So you look at the boundary of the positive part, and then you decompose it like into irreducible component. Every irreducible component should be also a positive geometry. Okay, so more concretely, so to define positive geometry, d-dimensional positive geometry, you have a pair that the x is a nice complex projective variety, okay, and x plus is a subset, the real subset, which is a semi-algebraic subset. And then it has also this nice property that whenever you're looking at the interior of this positive part, so that's orientable. Okay, and the positive geometry comes with a nice kind of unique top degree rational form, denoted by this omega x plus. So that's called the canonical form of the positive geometry. And again, this top degree rational form has this property that its poles are all simple, so they always happen like along the boundary, like along this x positive, and also the singularities are also recursive, meaning that once you are looking at the boundary components, the irreducible components of the boundary, and you want to, because they themselves are positive geometries by definitions, right? So every irreducible component of the boundary is a positive geometry. So you look at these irreducible components, they have this top degree rational form, and you can compute the canonical form of this component by taking the residue along those boundaries, the residue of the canonical form of the original object along this boundary. Okay, so and these positive geometries are kind of defined in a sense that they include Amplituhedron as an example, polytopes as an example, and also many other kind of geometric objects such as associohedron, etc. Okay, so what are the properties of these positive geometries? So you have this geometric object x plus, and you can define again the subdivisions of these objects. So what does that mean? So you would like to find, other positive geometries, so like smaller positive geometries that they cover a dense subset of this space. And also these subsets should be kind of compatible. For example, the interior part of every positive geometry is orientable, and you would like the orientation of these small pieces to be compatible with the orientation of the larger space. Okay, and the idea is that if you have a subdivision of your positive geometry, so then you can compute the canonical form of the positive geometry in terms of by taking summation over the smaller pieces. Okay, for example, if that's a cartoon picture, that if I have a positive geometry subdivided into 5 pieces, so then I can define, so each piece is a positive geometry, has a canonical form, and I can take their sum to get to the canonical form of the original object. Okay. And the second property is that whenever you have a diffeomorphism from x plus to y plus, so you have this nice map. So you want the canonical form of the image to be computable, like as a push forward of the canonical form of the original space. Okay, so again, so we are doing like all this for Amplituhedron because that's going to be like an example of positive geometry. So namely, you can take a subdivision. So we said that, the Amplituhedron, so the idea is to decompose the Amplituhedron in terms of positroid cell images of positroid cells, right? So let's say, so I have a collection of positroid cells whose images cover a dense subset of the Amplituhedron. It's a subdivision, so it has these nice properties. And by the second property, so the canonical form of the positroid cell and the canonical form of its image are equal, let's say, so they can be computed from this push forward of this canonical form. And also, you can write down the canonical form of the Amplituhedron as a sum of the canonical form of this positroid cell that they cover the Amplituhedron. Okay, so now you see that if you have different subdivisions of the Amplituhedron, so these different subdivisions lead to different ways that you can compute the canonical form. So like knowing various subdivisions, so you have basically more possibilities to do these computations. Okay, so yeah, so so I said, like, in order to look at the kind of the Amplituhedron case, in particular for these polytopes and conjugate to polytopes, so it makes sense to study the fibers of the map defining the Amplituhedron. And this study has been motivated by the geometry of fiber polytopes introduced by Bilera and Schrammfels, that actually has this secondary fan as a secondary polytope as a particular example. Okay, so here, so let's say I have a polytope in m-dimensional space in Rm, and then it has n vertices. So then you can look at the simplex with n vertices, like in Rn, and then this comes with a natural map, which let's denote this by pi plus, which takes the vertices of your simplex to the vertices of your polytope. Okay, so the idea is that you can extend this pi plus to like another map, another linear map from the spaces that the delta n leaves from Rn to Rm. So you have this map between the vertices of these simplices. You want to extend it to a linear space that they leave. Sorry, to this Rn Rm space that your polytopes leave. And then the fiber polytope is defined, the fiber polytope of delta n and p, by taking certain like integrals over the fibers of this map. Okay, and then actually you can define this fiber polytope. So they defined the fiber polytope for every pair of polytopes q and p. You can play the same game, but then what is nice is that in the case that you take delta n, so this fiber polytope is actually the secondary polytope of your original polytope P. In a sense, if you take this fiber polytope and then look at the normal fan of this polytope, so you basically see the secondary fan which encodes all these subdivisions of polytope. Okay, so now the idea is to study the same fiber geometry for Amplituhedron instead of polytopes, to extend this to these objects that are not necessarily polytope. So to do this, so we take like this map pi plus, which was the defining map of the Amplituhedron from positive Grassmannian to the Amplituhedron, and then we define it to a rational map from Grassmannian Kn to Grassmannian K plus m, because they live in these spaces, right? And then you can find like an explicit parametrization of the fibers, and by that I mean you take like any point in the Amplituhedron and you look at the pre-image under pi, pre-image under pi plus, and you can find parametrization of these points in a sense that you can explicitly say what are the elements of these fibers. Okay, so and the idea is that for every element, for every point in the Amplituhedron, so what you obtain, so these fibers are themselves positive geometries. Okay, so in particular, so they come with this unique top degree rational form, the canonical form. We would call this fiber volume form for now. Okay, and then you can use these fiber forms and take, certain residues of these forms, sum them up to get to the canonical form of the Amplituhedron. Okay, and even more, if these fiber volume forms are nice, for example, if the denominators of these forms have the denominator is just a product of a bunch of linear forms, so then you can say more. You can, because if these are product of linear forms, like for every linear form you have a hyperplane. Basically the form corresponds to a hyperplane arrangement, and you can use this hyperplane arrangement to construct a polyhedral fan which encodes all subdivisions of your Amplituhedron. And this is indeed the case for polytopes and for conjugate to polytopes. Okay, so now let me again go back to this computation of this canonical form of the Amplituhedron. So of course there is this analytic procedure that to compute the canonical form, you would take like the integral over some contours, integral of some rational forms over some contours, and then there is this geometric procedure that we saw that you would triangulate your Amplituhedron, and then you would take the sum over these triangles, and then you would compute the canonical form. And somehow, if you see, then these different contours are correspond to different sort of triangulations. Okay, and this work is, I should have said this before, but this work is motivated actually by this nice paper by Faro, Lukovsky, Parisi, that the title of the paper, I think, is Jeffrey-Kirwan residue meets Amplituhedron. And they looked into these canonical form of Amplituhedron for the polytopes and their conjugates, and they relate them. They computed these canonical forms in terms of these residues, taking the JK residues. Okay, that I will define now what are these residues, but for now you can think of them as some operations on differential forms. Okay, and the goal is now, you have this, you can already compute this canonical form of this fiber, so we would like to use these JK residues and use these forms of the fibers to construct a secondary fan for these conjugate to polytopes. Is there any question? Yeah, please stop me if you have any question. Okay, so so now let me recall what is the notion of Jeffrey-Kirwan residue. So basically, you can define them for every rational differential form when the denominator is just a product of some linear forms. Okay, so you have this is like a degree. This is an R degree rational form with n linear forms as a denominator. And then the idea is to look at the coefficients of these x variables, or if you think of them as hyperplanes, these linear forms define hyperplanes. You look at the normal ray of these hyperplanes, and then you look at these normal rays, and then you can construct a chamber fan of these rays. So basically, you have these rays, and then you look at the collections of these R rays, and then the cone generated by them, etc., etc. So you have this polyhedral fan. Okay, and to define the Jeffrey-Kirwan residue, you would the definition is based on when you fix a reference vector in your polyhedral fan, and once you do this, so the Jeffrey-Kirwan is defined as the sum of residues of your form along certain cones containing this reference vector. Okay, so what are those cones containing this reference vector? For example, here in this picture, so of course you have these 2, 4. So the cone generated by the rays 2 and 4 contains this reference vector, and the cone generated by 4 and 5, right? And also the cone generated by 1 and 2. So they all contain this reference vector, and in particular this region. Okay, so now you take the residue along these cones. Okay, so I haven't told you what means to taking the residue over the cone, but we will see this in the next example. Okay, so that's the definition of Jeffrey-Kirwan residue, and I should say that in the classical definition, so these are all these rays or all these hyperplane arrangements corresponding to them intersect in a common point. For example, you wouldn't have these AIs, so it's a bit of it needs a little bit of work to kind of work out the classical one to this setting that you're allowing to have these AIs to be non-zero, and then you're allowing that some of these hyperplanes are not intersecting in the same point. Okay, so here is an example. Let's take the polytope pentagon. So these fiber volume form after parametrization, so they would have such a structure. So this is a 2 form, right? And then again, if I take the rays corresponding to these denominators, so I would have such a picture. And then the Jeffrey-Kirwan residue is the sum of the residues of 3 triangles. Okay, somehow every such cone corresponds to 1 triangle in this picture. So for this cone 2, 4, so I would look at the complement of 2, 4, complement which is 1, 3, 5, and that gives me this triangle. So every such region corresponds to 1 triangle. And the second one for 4, 5, I look at the complement set, which is 1, 2, 3, and that gives me like the second triangle, and etc. So I have the residues of each of them, and then we need to sum them up, and then we get the residue of the form that we were interested to compute. Okay, and then if you take points, like different points like in the same cone, so that would lead to the same residue, to the same triangulation of the polytope. And then if you take points like in different regions, so that would correspond to different triangulations of your object. For example, here, so I have taken my points to be like in a neighbor cone. So that's why I got like another polytope, which is actually, you can see that it can be obtained by just kind of swapping the 3, 5, and 1, 4. So the neighbor cones are somehow corresponding to neighbor triangulations in the secondary fan. Okay, and of course the equality.
Can I ask a question?
Yes, sure.
Is it true that these fiber volume forms are just, so you had this formula for the integral and the contour, right? And there's some top form on the Grassmannian, and then some delta functions there, which fix some of this element in the Grassmannian. So is it true that the fiber volume form is just this, the top volume form, after you solve all the delta functions? Or do I understand properly?
So. Yeah, I think you're right, yes. Yeah.
Okay.
So you can explicitly write them down in terms of the form that you have chosen for the Grassmannian.
Okay, thank you.
Yes. Mm-hmm. So yeah, so I mean different, so I was just saying that different points, different reference points lead to different description of these JK residues, but of course they're equal because of the global residue theorem. And then if you choose your reference points from different cones, from neighbor cones, that would be corresponding to certain flips of the triangulations. Okay, good. So, and then what we saw is that if you, so this is in general, but then when you're, these fiber volume forms, they only have poles along some hyperplanes, or they're somehow their denominators is the product of linear forms. So then we can use this Jeffrey-Kervan residue to compute somehow like the canonical form of these objects, and also the canonical form of the amplituhedron. Okay, and this is the case for the polytopes and their conjugate to polytopes, and in particular, so these hyperplane arrangement that you have, and also the normal rays of this hyperplane arrangement defines a fan, so the same fan that we saw like in the previous picture, and this fan, let's call this like FAY, and then we show that this fan is actually the secondary fan of amplituhedron, so encodes all these subdivisions. Okay, but to show that this is well defined, so this is a well-defined secondary fan, so we have to take somehow different points in the amplituhedron, and then kind of compare the combinatorial structure of this fan that we constructed. And then you see that these are combinatorially, they are equivalent. And that's what I mean by having a well-structured notion of secondary amplituhedron. Okay, so let me just repeat to make sure that I didn't miss like any part. So I have chosen like y a point like in the amplituhedron, and with this y, I chose like a parametrization of this y. I computed a kind of fiber volume form, and then I looked into the fiber volume form, the denominator. Then I constructed like a polyhedral fan, like as a chamber fan, and the claim is that if you take different points and then go the same procedure, you get to the same fan combinatorially, and then this fan encodes like all these subdivisions of the object that we were interested in. Okay, so and of course the question is whether you can do this for other amplituhedrons. So the good thing here was that the denominators were product of linear forms, and then we used them. And then we use them to somehow to apply this Jeffrey-Kervan residue to our setting. So if you can come up with another way to compute the residues of these forms and kind of extend the results of Jeffrey-Kervan residues from hyperplane arrangements to somehow somehow like hyperplanes or curves, like different kind of geometric objects that they are defined not just by linear forms, but maybe by quadratic forms, etc., etc. So then you can apply the same arguments to kind of construct such fans for the subdivisions. Okay. So, okay, and then here I just wanted to show you that in general, for every amplituhedron, you can write down this nice parametrization of the elements of the fiber. So basically for every point in the amplituhedron, once you fix your Z, the defining matrix of the amplituhedron, you can look at the different fibers like this pi plus inverse and pi inverse, and kind of work out, you know, when like a matrix represents an element of the pi inverse and pi plus inverse. And once you have this, so then you can use, then you can compute these the volume forms of these objects. So now let me give you like another example, which is not polytope, so it's conjugate to polytope. Sorry, in this case, it's actually again like a polytope, but that's conjugate to pentagon. So you have fixed your Z, and then let's say I have taken like a specific chart, and then I have parameterized my pi inverse Y. Okay, so then I take this form, so that would be the corresponding form of the fiber. So I look at the denominator, so they are linear forms, and then I construct these rays corresponding to these linear forms, and then I construct the, you know, the polyhedral fan defined by these rays as a chamber fan. And then you can see that you can do this, you can play the same game and compute the different triangulations of your amplituhedron, and then you can see that these triangulations are actually parity dual to the triangulations of the pentagon. Okay, and now going back to the general picture, let me just recall, you know, what we saw in the beginning is that so the idea is that the general picture that we would like to have is that you have two positive geometries like x plus, y plus, okay? And you have this map from the positive part of x to the positive part of y. And then let's say you know something about the original space, for example, you know its triangulations, you know its canonical form, it has some nice properties, and then you would like to understand the image of this pi plus, and then see what sort of information can be transferred from the original space to this y plus. So that's the idea, that's the question. And somehow like the approach here was that we are looking at, we are extending this map to the larger space that they live in, so from x to y. So we are looking at this pi plus, the extension of this pi plus to this rational map from x to y. And then we are looking at the fibers of this object, and then you know, you can try to understand the fibers of different points, like in the second space, and then see whether whether you know they have these nice positive geometry properties as well. And if that's the case, so then the question is, what is the residue procedure on these fiber volume forms that kind of led us to compute the canonical form of the y plus? Okay, so now the questions, what I'm phrasing is like in more general. I think it can be studied like in more generality, not just in terms of the amplituhedron, but maybe for every positive geometry we can do this. Like if we can say, if you understand the fibers of this map for positive geometry, so the question is, can we use these fibers to compute the canonical form of these objects? And as we saw here, so these fibers, kind of the denominators of these fibers defined like the polyhedral fan, which encode these subdivisions. So the question is whether these sort of nice families of subdivisions you know, exist for other families of positive geometries. For example, you can start, as I showed before, so you start from any pair of polytopes Q and P, and then you can construct these fiber polytope by going through construction of Bilera and Schronfels, and it's quite like easy in that setting to see that the canonical form of these fiber polytopes are kind of related to the canonical forms of the original polytopes. So the question is whether you can see this even more for other families of positroids, that you have something, you know something about the Original positive geometry is triangulation, this canonical form, but you want to understand the image by looking into these fibers of this image. Okay, thank you so much. So I stop here and please ask me questions.
Thank you. Let's
Thank
take
you.
Fatemeh for the talk. And do we have some questions? So I open the floor for questions. I see Yara.
Yeah, I have a question about this dual case for the polygon that you asked before. So do I understand correctly that the triangulation in terms of the original would be like the external triangulation?
By dual, you mean the conjugate of the polytope?
Well, the case that you showed, yeah. So you said that you would triangulate the dual polygon. So my understanding is that in terms of the original polygon, that's the external triangulation. If I understand the dual in the right way.
So,
yeah.
Okay, so
Or, can you say what the triangulation would be?
So you mean like here, for example?
Yeah. Yes.
Okay, so what is already, you know, like in this work by Galashin and Thomas Lamb, I think there is this kind of bijection between the triangulations, right? So now the idea is here, I mean, you can concretely write down the fan, right? So you look at it, I mean, we have, you can construct by parametrization, you can write down the volume form, and then you look at the denominator and construct this polyhedral fan. And once you have the polyhedral fan, you have exactly these triangulations. And in this case, yeah, exactly. So, I mean, that's how I know that, I mean, so this is like, so this triangulation is in terms of these three kind of positroid cells, right? And then you have the concrete description of this positroid cell, if that's what you mean.
Maybe I can make a comment. So I think there's a difference between duality and polarity. So I think, Jaroslav, you're speaking about polar polytopes in the same
okay.
And here, what Fatemeh is speaking about is duality. These are in different spaces, complementary.
All right, I see. It is 5-2-2, not 5-2-1. Yeah, so yeah, right.
Yeah, okay, thank you. Yeah. Also, you were talking about the dual as the dual polytope, right? Yeah. Okay.
I think these are always internal triangulations from that point of view, Yara.
They're
all
like
ordinary. They're like images of positroid cells, not things that are outside in that point.
Yeah, but maybe related to it, is there any way how to get a triangulation with outside triangles? When you use some points outside to triangulate the...
Okay, so now you're asking again about the dual in the sense of polytope, right? So you have a polytope, you know its triangulation, and then you're asking about the triangulation of the dual polytope.
Yeah. Well, yeah, it would be a triangulation of the dual polytope, but in the original polytope, it would correspond to some triangulation which is not internal, but like external. So you are using some points outside to triangulate the whole thing by like basically subtracting triangles rather than adding. Does that make any sense in this picture or not?
Yeah, I'm not sure. I don't really understand what it means to take like external points and triangulate. I think the picture you have in mind, maybe you have a polytope and then you have a larger polytope and then you kind of subtract some part of it, right?
Well, for example, the easiest thing is if you have a simple polytope, like let's say you have a polygon. You take the polygon and then you just draw a line far away, and then from every vertex you extend the edges away from the vertex to get a triangle. To get a triangle, including this extra sort of line that you put out infinity, and then there's an inclusion-exclusion sort of triangulation of the original polygon in that way. That's what these. I mean, that picture that we just described is exactly the polar dual of taking the dual polygon with a point in the inside and then just triangulating in the obvious way, you know, attaching little pizza slices to cover the triangle. So the pizza slice triangulation of the polar dual polygon is this funny inclusion-exclusion sort of triangulation of the original polygon. And in the story of the Amplituhedron connected to total positivity, I mean, connected to the positive Grassmannian, only gives you one kind of triangulation, Yara asked this question because a number of us have been fantasizing for years and years about some kind of dual of the Amplituhedron. That's the analog of the notion of polar dual for the polytope. And the natural sort of triangulations or formulas you'd get for the form look more like the sort that Yara was just talking about, which is why at every opportunity when people talk about triangulations, you can be guaranteed that Yara will ask some analog of this question. Broken record, you know, over and over and over again. Anyway,
can I make a comment here?
Yeah.
So Yara, the thing that you just said made me think about the kind of the work that Lionel and Heslop had done a while ago. I think you were probably involved in this as well with the coralhedron or the amplituhedron squared, that paper that came out several years ago, if you remember. And so I've looked at this a little bit. I mean, when you take that point from going from the inside the polytope to outside the polytope to do this, you can actually incorporate a lot of that structure in. And the unfortunate and the disappointing thing that I found there is that when you start incorporating that into the Grassmannian, you leave the positive geometry into the total Grassmannian GRKN plus 1. And then things become really ugly because they're unorientable. I don't know if that's
yeah, well, there was
more of an observation than anything else.
Yeah, there was definitely a problem that this triangulation that Nima mentioned, this pizza slice putting on inside, kind of didn't work for higher K. There was no way how to put kind of point inside more than K equals 1.
So, but I mean, you can, I don't want to say it doesn't work. I think it works as long as you have to be a little bit more flexible. But it's, yeah, you can still think about that point existing. And here KN, you get a good triangulation, a good positive geometry of the KN, but once you add that extra point in, you start having to look at things called a cousin of the matroid stratification that Fatemeh talked about called Deodar stratification, and you can still construct a very similar story. Things get ugly, as I said. Non-orientability rears its head, which is some of what Heslop Stewart identified. I don't know. There's something there that I would love to poke at some more.
Yeah, but I think that in this case you'll never get something like an external triangulation because these decompositions are always into images of positron cells, so they'll be always inside. And yeah, I don't know if there's any way to make them somehow talk about some external parts. So yeah. I would say that that's not possible in this context. Can I have a question related to this conjugate? So already in the paper with Lita and Mattel, we wrote some story for the conjugates as well and for the Jeffrey-Curran residue. Is your form different than the one which we suggested there? I mean,
it's the same. So we have I think we have a remark like in our paper saying that these are exactly like different description, but this is the same.
So the form is the same. So you do the same as you explained before, that you take the top cell of the top cell form of the positive Grassmannian, you solve the delta functions, and then what happens is that you get some number of linear terms in the denominator, right?
Yes.
Okay.
Yes, exactly. Yes.
So how to extend this beyond K equal to 1 and the duals? Any ideas for either of these notions to be extended, either Jeffrey-Curran residue or Gale duality, or I don't know in which direction to take it, but
yeah, I think the way that at least I would like to think about it is like looking at this kind of generalizing maybe this JK residue computation from this hyperplane arrangement to something for higher dimension, that you have these curvy objects. So the defining the denominators are not necessarily linear. Maybe you add one quadratic forms, etc. So that would be the way that I have thought about this, but no result yet.
But have mathematicians considered this kind of generalizations? So I'm not familiar with it, but maybe we have a lot of mathematicians in the audience.
I mean, we haven't seen like anything. So for example, there is this notion of fiber, fiber geometry for convex bodies that they're beyond like these polytopes. But again, we couldn't make a connection with what we need here. But maybe others can comment on that. Yeah, there are very recent papers like on fiber geometry for convex bodies, but in a different, maybe in different setting.
What is the relation of a convex body to a positive geometry? I'm not sure what the convex.
No, I don't think there is any. I mean, I don't think they have made like any connection with positive geometry. I'm just saying, usually you define. I mean, these fiber geometries. So these are kind of. This has been started by work of Bilera and Schronfeld, right? That you would consider the fibers of polytopes. So I've seen that like instead of polytopes, so they take like convex bodies that they're not necessarily defined by linear forms, but they're by higher degree. Kind of forms, and they have tried to kind of define this notion of the fiber geometry, but they haven't looked at them like in details, and I don't think these are kind of it's like immediate like to apply them here.
So I'd like to follow up on this question. So my question maybe for the experts, Nima and others. I mean, what's the relationship where if we replace polytopes by other convex bodies, for example, spectrahedra, the non-negative orthon becomes the cone of positive definite matrices. Are there natural positive geometries in that setting? Non-polyhedral convex bodies.
I don't know specifically about the spectrahedra example that you brought up, although I remember looking at it for some reason a long time ago. I don't remember the answer. Of course, there are other curvy settings where you get positive geometries. And I think actually even sticking inside the Grassmannians, but just asking for more general external data other than positive external data. I mean, Thomas defined these sort of general Grassmann polytopes as the images of the C.Z map, where you ask the Z data as general. You don't ask for it to be necessarily positive. Experimentally, we looked at a few examples like that, and they are positive geometries. You can find the corresponding canonical forms, but how to think about them, even inside G25, is I think an open problem. There are cases where I mean it's not guaranteed as far as I can see. It's not guaranteed. Well, not just as far as we know, it's not guaranteed a priori. If you just plonk down a bunch of nonlinear equations and say this cuts out a space, it is most certainly not guaranteed that it gives you a positive geometry. We see that already on the plane, where, for example, if you cut out a little teardrop using a cubic curve, that's not a positive geometry. Despite the fact that it has codimension 1 and it has an edge and has a vertex, it's not a positive geometry because we have non-zero forms that are well defined on the boundary. Just the dx over y form is defined on the boundary in that case. So you can't have a unique canonical form because you can always add this non-singular form. Sorry, but we have non-singular forms. There isn't a unique canonical form associated with it. Anything in the plane, I think even sort of just trying to classify properly in the plane, one of the most general positive geometries that we can have cut out by polynomial equations would be an interesting thing. Clearly, you can do it with like linear factors and quadratic factors, like one quadratic factor and a bunch of linear factors, no problem. But does it start going to hell when you have enough quadratic factors? Probably, I imagine. But trying to understand that, even in that case, I think is a very nice problem. And the general Grassmannian generalizations or general Grassmannian polytopes that are not the analog of cyclic polytopes, but just with general data is another nice question. And maybe I could both ask. Well, I'll mention another thing. And many people here have done a lot of very nice work in this general neighborhood. But the M equals 2 amplituhedron is not a polytope, but is the most polytope-like of the amplituhedra somehow. I still don't know whether there is, especially the sort of connection with the hypersimplex, suggests that there is some actual direct map or bijection between literally a polytope and the m equals 2 amplituhedron. But anyway, it's very polytope-like. And one feature of this is that it's possible to cut out the m equals 2 amplituhedron, and this is all conjectural. Maybe it's not a conjecture for m equals 2, I can't remember, but it's certainly conjectural for even m in general, that one can cut out the amplituhedron just by inequalities. But for m equals 2, there are inequalities that involve the sort of the minors made out of just y. So they're of course they're quadratic. They're not nonlinear just because it's a Grassmannian statement, but they're just linear statements about the minors y. So it's just this statement that what we call y I bar j bar is positive. But you can actually say it geometrically nicely, which is that if you imagine taking the external z data, then for any k for m equals 2, if you look at the 3 consecutive points, zi minus 1, zi plus 1, so that gives you a plane. That plane will intersect y, which is a k-plane in k plus 2 dimensions. Zi minus 1, zi plus 1 intersects y in a point. And so we can now look at all of those points inside y. So we have, if I call this point zi minus 1, zi plus 1, and where it intersects y, if I call that w, there's some w1, w2, w3. So we have all of these w's, n w's that are just points in the k-dimensional space of y itself. And the conjecture is that y is in the amplituhedron if and only if that configuration of n k-dimensional vectors is positive. So we have all of these minors that involve y intersecting with zi minus 1, zi plus 1 are positive. So conjecturally for m equals 2, that cuts out the m equals 2 amplituhedron just as these linear statements about the minors. And there's an analog of that conjecturally for higher m that would now start using determinants of these minors and so on. So it becomes nonlinear already at m equals 4. But for m equals 2, it's just linear. And so my question is that if we start with that sort of model for the amplituhedron, maybe that's that's as close as we can get to the linear inequality way of cutting out polytopes. And perhaps the sort of program that you're talking about sort of directly works in that or could be realized exactly in that case, in the closest analogy to ordinary polytopes.
Hi, Nima. I just wanted to say that I realized that actually after we discussed this last time, that we define these vectors at the intersection of y with these planes in our paper with Fatemeh, actually, in a sense that we actually, these vectors were playing a role of the secondary fund for the parity conjugate to the dual. Okay. So somehow, and basically for
m equals 2 or for any m?
For any m. But for the parity conjugate only for the parity conjugate.
I see.
No, the thing is that basically I think they could be used to define some Gale dual. I have suspicion because like the minors that you're talking about were actually the determinants of these cones in this fund.
Sure.
But like I was just looking at now, and these are exactly the vectors you were telling. So I think that could be you're right. That could be a good starting point. And the positivity that you're telling about the amplituhedron reflects some conditions of how these funds are, which are the secondary funds. So I think that it's a good starting point to have a look at there.
Yeah, this thing that I'm saying only works for even m. And then for m equals 4, you'd have to look at the 5 plane that you make from I minus 2, I minus 1, I plus 1, and so on. Yeah, okay.
Can I have one more question to Fatemeh? Whatever your construction for odd m, it's what Nima said, right? Everything works nicely usually for even m, but what about odd m? Are you also able to find polytopes and then the answer using it?
I mean, if I'm not mistaken, I don't think we have any assumptions on the m Maybe Matteo can correct me, but I think this, I mean, what I was talking about, I think is for general M, right? So we don't have like any.
I mean,
sometimes we use the, we use some of the results in the literature, of course, when know we talk about this parity duality of.
So the parity duality is for even M. Yeah, it was only for even M.
Yeah, because already in our paper with Matteo and Livia, we noticed, we observed that for odd M, this JK residue is behaving very strange way. So I think that. So I was just wondering whether the fiber polytopes are still possible to define for odd M.
I think the problem with the fiber polytope could be that the polytope might not be convex, and so in that case, you're computing the fiber polytope of the convex hull of the points, which is not the polytope you want. And so I think that would be the problem in case.
You mean in the polytope case, not in the. You're muted.
Sorry, I was muted. I was saying that in the polytope case, you might have that the polytopes are not convex, and then this construction is working with it's based on Gale duality, and it's basically building the triangulation, the convex hull of points. And so if you're considering not convex regions, that this wouldn't work, I think.
Yeah, so we know for m equal to 1, for example, all these objects are concave. I mean, they're not convex at all. So
exactly.
In that case, the fiber polytope is not a fiber polytope of an amplituhedron. It's a fiber polytope of the convex.
Exactly.
Convex hull. Okay.
Can I ask another basic question, guys? And I apologize, Fatemeh, I missed the first half of your talk because I had another meeting that I couldn't push off.
You didn't miss much.
So sorry if you first, sorry for that, and secondly, sorry if you explained this already in that part of your talk. But since you quickly alluded to it, maybe you or one of the other people who knows the answer could tell me. So there was this for polytopes. There is this sort of nice, this kind of Grassmannian formula like way of defining the canonical form by the contour integral. This sort of dc over c formula where you just add an I epsilon to all of the denominators, and then that's the kind of so that specifies a contour, if you like, right? You say exactly which contour you're talking about. And then the different ways of closing the contour, at least in examples, it's clear that the different ways of closing the contour and continuing to do this until you're done gives you different triangulations of the polytope. What's not obvious to me a priori is that you get all triangulations of the polytope in this way. So I guess my question to you or any of the experts who've looked at this, is it true that all the triangulations of the polytope, I mean the ones that are based on the vertices, of course, do they all arise in this way, or do you only get some class of them in this way, or
regular?
What's the relation between this contour integral picture and the stuff that you're talking about just for polytopes?
I think you get all of them, but you know, this secondary fan structure, so this fiber fan structure only works for regular triangulations, right? Like in the polytope sense, regular, I think, so perhaps you know what regular means, right? Regular in a sense that, you know, you lift them up, you lift the points like by height, and then you
right. They're all sort of images of the downward pointing facets when you lift everything up.
Yes, exactly.
Right.
Yeah, I think it would be interesting in general to look at the triangulations. I mean, also not regular, or even not regular triangulation. I think maybe Bern had a work on this generalization of fiber polytopes for non-regular triangulation as well, or something. But I don't know, because in the Amplituhedron in general, you're also interested in something beyond the regular triangulations, which for m equals to 2, they were kind of the one coming from the tropical positive Grassmannian, right? So, but there's like many more, and those are just a small part. And if you want to compute the canonical form, you don't actually care much about regular triangulations or not. So that's.
But did I understand correctly that, Nima, you said, so like in this, once you do this contour computation, you also get this non-regular one for polytopes?
I don't. Well, I think all the examples I know are too small to see the non-regular ones if they're there. So I don't actually know. But that's where I was actually throwing the, well, that was really the substance of my question. Do we really get all triangulations, just the regular triangulations, or are we even missing something more than that? Yeah, that I ask only because if that connection is really tight, it would motivate going back to something that we've tried a few times, but not tried terribly hard, I have to say, to just try to make another guess for what that contour is in general. I mean, it's not something as dumb as just adding as a simple I epsilon prescription, but maybe if I remember now, I think at least for n equals 2, we had some ideas about what the sort of correct contour should actually be. Yeah, I'm just sort of asking for if the connection is really tight, then it suggests that one should find some analog of this nice contour to talk about for general M and K. Mm-hmm. So that's why I wanted to know if it's not tight even for k equals 1, then forget about it. But I thought you were saying that you thought you got all the regular triangulations in this way.
Yes, that's correct. Yeah.
And also, again, related to Yara's question, this contour integral formula, where you just add these I epsilons, is conceptually identical to, I mean, or it comes from, or is directly related to, by a simple Laplace transform or Fourier transform, depending on how you want to say it, this dual volume formula. So for polytopes, we have these, like, of course, you can always talk about canonical forms by triangulation, but it's not, of course, obviously, it's not an especially intrinsic or beautiful characterization of what the canonical form is. For polytopes, we have a sort of two different intrinsic pictures for what the canonical form is. One of them is the volume of the dual polytope, and it's really concretely that formula that we want the analog for general M and K. Even for M equals 2, we don't have the kind of analog of this picture of the dual volume. And there's a very concrete indication that such a formula should exist, because even for k equals 1, there is something which, from the perspective of the triangulations you're talking about, looks miraculous, which is that the canonical form is actually numerically positive when y is inside the amplituhedron. Okay, so when y is inside the amplituhedron, or if you like, it doesn't change sign anywhere. It has poles on the boundary, but inside it, if you like, the denominator is all positive, but the numerator is positive as well. That is a fact which is observationally true, but it is not true term by term in these triangulations. Term by term in the triangulations, you can have plus and minus signs, but they all add up to something positive. Of course, the reason for that positivity is that it's the volume of the dual, and that volume is manifestly positive. What we've observed in every known example related to the amplituhedron is every time you ask any question, whether it's about it's always the case that that when y is inside the amplituhedron, the object is positive. The answer is positive, and in every presentation we know of, that positivity is the result of a huge cancellation between plus and minus signs that gives you something slightly positive in the end. There must be some picture that makes that fact obvious. It's a very striking fact. There must be some picture that makes it obvious, and that's what the dual amplituhedron, the polar dual of the amplituhedron, if it exists, should make that fact obvious. But the reason I keep coming back to this question is already for k equals 1, we have a few consequences of this fact, a few presentations of this fact. One of them is the direct formula for the canonical form as the volume of the dual. The other one, though, is this contour integral formula, where you can close the contour in every possible way to get all the triangulation. Since we don't know exactly what we're looking for higher k, we should grasp at straws for anything that we do understand and try to push where it might generalize to. So anyway, so if there was a picture that sort of gave you the contour for general K, the generalized beyond K equals 1, that may well be the sort of clue for finding this dual formulation that we're looking for.
Yeah, I'd be definitely interested, to look into this duality that you guys are talking about. So I haven't looked into this.
And maybe I can just say one thing about the sort of challenge of this notion of the polar dual is you see it already in the positive Grassmannian. It's not a problem with the Amplituhedron. It's really a problem or an issue, challenge, whatever you want to say, with Grassmannian positivity. Because if you think about the positive Grassmannian as a sort of Grassmannian generalization of a simplex, well, the simplex has the lovely property of being its own polar dual. Okay, so the dual of a simplex is a simplex. And so you see that reflected in the facet counts and so on. Well, beginning with the positive Grassmannian, the polar dual, if you just take the facet count for G24 and you turn it upside down, it's not the same as itself. G24 has 4 codimension 1 boundaries. Positive G24 has 4 codimension 1 boundaries and 6 codimension 0 vertices, right? 6 codimension 0 boundaries. And so it's just not the same when you turn it upside down. So whatever the notion of duality is, has to somehow, begin with this basic difference that even the kind of the Grassmannian simplex, which is the positive Grassmannian, is not self-dual. So I don't know what the correct notion of duality should be, but in a sense, the challenge is sitting there already for the Grassmannian itself.
Is there any subset of the Amplituhedron that you can define which has this property that the boundary poset is isomorphic to its
Not that I know of. Not that I know of. I mean, maybe if one degenerates the external data in some way, maybe it could happen. But
because this doesn't happen for generalized triangles, as far as I remember. And those are the most the nicest things that are similar to. Well, maybe for the chamber side, to the chambers that in Amplituhedron, but that's not. Yeah, they're not simplices anyway. So yeah, okay.
Yeah, sorry, I didn't mean to hijack the discussion to one about the dual, but since it's never far from my mind either, I apologize.
It's fine. I think that some of us are thinking about this.
Yes, I know. Yeah, I made the mistake once of saying that only 2 people care about it, and the other 2 people who care about it were in the audience. So 4 of us care about it.
Yeah. So do we have some more questions?
Yeah. Can I ask you, Nima, do you have any reason for believing that this positivity property that we see in the Amplituhedron, that the fact that the canonical form is positive inside the Amplituhedron holds for canonical forms in general, the canonical form is positive inside the positive geometry?
It's not true in complete generality. In our paper with Thomas and Yantao, I think we defined we used the word sort of convex positive geometry or something like that, exactly to restrict to that to the more special set of cases where this phenomenon happens. It's not true in general for a general positive geometry. Okay. I can't remember the counterexamples right off the top of my head, but we gave examples in the paper of things that are not positive in that sense.
You can just take a non-convex polygon in the plane where the sides of the polygon intersect the interior, and as long as the sides of the polygon intersect the interior, then it will change signs in the middle.
Yeah. Okay. If we take a kite shape like that, that counts as a positive geometry, but it does not have a positive numerator. Yeah.
Okay, I think that we should finish the discussion now, and thank Fatemeh once more for her very nice talk. So,
thank you for that.